Hello everyone. Today, Professor Stefano, he is professor from USA. He completed his PhD from Italy, and he has a vast experience in Italy and more than 20 years including Switzerland, Italy, and you can say now in the United States. So, thank you very much, Stefano, for your precious time to join this session. So just to guide our youth for the career, and you can say the Stefano is a professor in USA, and his area of expertise is actually in the data science and something you can say data systems and advanced engineering. So Stefano, just for the you because you based before starting the questions, some questions I want to ask about how you will share about the journey from diverse journey in Europe and then USA. Just I'm curious to listen from you and our audience as well, please.
Yeah, I did quite a journey from, my hometown, Rome, and then through Switzerland, Geneva, very international. And I've been working for this very large scientific collaboration at CERN. So very diverse, very large, and very international. And then moving to US, also quite a challenge. Uh, Different system, different people. Um, so I think this is a really something I suggest. So if you can travel and see people and connect and to kind of learn how to work with other different people with different background, with different culture, with different knowledge, with different expertise. I think it would be, it's in your best interest to kind of build this global network, and so to enrich your life and sort of to learn more.
Very nice, very nice. And Stefano, what engineering challenges were most rewarding during your work in different organizations? Still, you are currently working in USA.
Um, yeah, when I well, still, my CMS experiment at CERN. It's where I do most of my research. Um, I think in one word, I would say the complexity. I've been always fascinated by complex problems that are not uh, solvable in one way. So this complexity, the idea that there is a big problem and you can sort of solve it in so many ways. And probably there are many ways where this problem can be solved efficiently, and many ways where it might work, but in our experiment we're very concerned about the performance and efficiency of software, of firmware, of machines, hardware, and mechanics and everything. And so the idea that my experiment has to face something really complex really fascinated me and kind of was the initial motivation. And it's still now every day when I wake up, I'm still looking for a complex problem to solve. Sort of that's what, and I think every scientist would agree that it makes your life interesting. That there is something really um, that you have to think first, and then you have to talk to people, and then you have to discuss, and then you have to refine. So it's a sort of kind of something that makes you, it's stimulating, in one word. Yeah.
Very nice, very nice. And also your journey, you are because we have vast experience, and your Google Scholar shows H index more than 200, I-10 index more than 700, or the citations more than you can say 206,000 like that. So what do you think about this journey? This, if you brief those people who are very concerned about their citations, H index, I like that. So, what advice you will give to those peoples?
I don't think you should be concerned. Anyone should be concerned. Yeah, if you check those numbers, yeah, you can easily be better than Einstein. On paper, you could do that, but clearly I'm not. And so I think that has to do with the way we measure things that changed over time. What I suggest, maybe, younger students or people that are now facing science, not to be bothered by or concerned by like, oh, you have to deliver so many papers. Some institutions or some places, they sort of suggest you to do that sort of heavy publishing, but my point of view is it is better to write, sort of uh, conservatively, like you don't over publish. Nowadays it's become like an industry also. So it's not that complicated to sort of get it published, but maybe quality is more important than quantity, I would say, for your career, for your reputation, and for the connection you will do with people. So people will read the article, and if there's an article that is interesting, it is interesting. It doesn't matter if there are not that many citations. You will be known and you will be respected. So, but I agree that it's a little bit complicated the way we measure the industry sort of, or the science. It's measuring citations and sort of giving sort of numbers to people. Um, I suggest not to look at those numbers that much, and but focus on what we are on the challenge. Let's say, yeah.
Very nice, very nice. And about your work, for example, how did your role evolve from detector design to large scale system integration? How it evolves, something like
Yeah.
that.
Well, my background is really, yeah, sort of wide. I started with aerospace engineering and then physics. So I kind of started with detectors without a clear idea of how detectors is made and how it is constructed. And so over several years, I became sort of an expert of detectors. But yeah, in our experiment, a detector is just one part of the entire chain. So the entire readout chain starts with detector, so with reading out some physics, and then you need electronics, firmware, computers, software, and then a big sort of algorithm that is merging together all the detectors together with the data acquisition system to perform the data analysis. So I was interested, as I said, in the complexity, and so in the how different parts would interact. So the detector, I mean, I build detectors, and it's fun. I'm really an hands-on guy, so I like to build stuff. But I also love computers and the way computers can be programmed efficiently to sort of, yeah, read out and exploit the data that nature is giving. Um, and so, yeah, in different parts of my life, in different situations, I sort of worked more on detectors, on the hands-on part. And then maybe, for example, recently I'm more into computing. So how to sort of make it efficient and running in a way that, yeah, it's scalable, it's sort of error-free, and in general efficient.
Very nice. That's good. And what are the real world applications of technologies developed by for high energy physics or something like that?
Yeah, that's a very excellent question. Um, well, we usually tell the story of how the electron was discovered, and back then the electron was just a particle, and then but think about now the world without electricity. So electron unlocked electricity. So high energy physics is it's kind of the frontier of knowledge. So it's not that we discover something and tomorrow it's going to be usable, because it's based it's a physics that builds up knowledge, and eventually maybe in 50 years, maybe next century, we will find a way to sort of exploit what we find. But the other thing is that at CERN, for example, the technology we need to develop to make those discoveries, that's the key to make the world a better place. So like the World Wide Web was invented at CERN, for example. Think about now the value and the world without the World Wide Web. But other examples are tomography, imaging for medical applications, cancer therapy. So people build small accelerators for targeting cancer cell and then kill the cancer cell. And so just like as I said, advanced imaging. So all the scanners that we can build, uh, yeah, for healthcare, they're all sort of derived from technologies that we developed in the detector, but also the entire, as I said, software related efficiency and performance algorithms that we develop. Sometimes they get exploited and it bring innovation to the entire technology field, and so we all benefit from that.
Nice, that's nice. And if you want to elaborate on your experience with the clean room microelectronics, how you will say about this?
Um, So yeah, we use a clean room to build detectors. Some generations of detectors they would need a very specific clean room, and well, it's fun. It's hands-on, so it's something sort of I like, but maybe it depends. It's something that requires a very dedicated procedure. So very similar to industry. So detectors, we build detectors, but when we have more mass production, we have say hundreds of those objects. So we need to be very like precise. Very there's a very like dedicated procedure, what to do, what not to do, how to dress, how to screw all the parts, how to glue, how to mount, and so so yeah, I think it's fun as a student. Yeah, and working with students, it's a fun activity. That it's a good experience how to participate in such an activity. It's a lot of learning and a lot of hands-on task. Um, yeah.
There's no, yeah, good. And how do data acquisition systems for physics compare with the industrial QA system, something like that?
So I guess in our experiment, data acquisition systems are really peculiar because we have very stringent requirements in terms of timing, in terms of several constraints, maybe radiation hard, like environment. Our environment is like very dangerous and very unusual for industry because it's like there's a lot of radiation. And so the software and the firmware has to be very redundant and very fail-safe. But there are many like sort of similarities. As I said, efficiency is one of them. Like industry also focus the attention on exploiting resources properly. So I think we have a data acquisition. Well, we have several ways to acquire data, and it, of course, a complex mechanism. Like it's a giant effort that is carried out by so many people. So in that sense, it's very like international and very, I would say, team oriented. So in that sense, I think industry has a similar approach. Large team of people. Oh, sorry. They work on the same task, and so sometimes it's difficult to. It's a challenge also to get together on the same. Um, Not in the same room, but that the software doesn't crash. Yeah? Similar challenges as we see with open source code and with with giant software like operating systems or large frameworks of platforms. The challenge of getting so many people together and have an environment where things work without breaking anything.
Nice, that's good. And what do you think about the role of firmware development, which can play in detector performance, something like that?
Sorry, the role of
I mean, what role does firmware development play in detector performance?
hardware. So a detector is a very weird object, but in a way, it's very similar to an iPhone. So the detector has a hardware part, a firmware part, and a software part. And usually, when we design such a device, we always ask, well, they're all integrated, just like an iPhone. So the software, the designer has to make a choice. As we are gonna maybe put the functionality in the software, or maybe in the firmware, or maybe in the hardware. The hardware is more complicated to sort of develop, and it's once it is developed, it's done. Especially in our experiment where we install the hardware underground, and then we have no way to replace it or to change it or to upgrade it. On the software, we have more freedom. Of course, we can still do an upgrade. We can push an upgrade, and we don't need to go and dismount it. But of course, with the software, there are other problems. It's less performant. So at the very beginning, before we did, we sort of develop anything, we ask ourselves what are the different roles or the different parts. So it's very, yeah, it takes you can some sort of creativity and sort of thinking out of the box kind of skill to sort of decide what to do. Just like similar to industry, when you have full control of on a device, hardware, firmware, software, how to implement it. Because as I said, the complexity is where you have so many different solutions, but you have to sort of decide and get agree on just one. And so you have to make sure that that solution that you go for, yeah, it's the one that makes sense.
Very nice. That's good. And you have worked in different organizations in Switzerland and USA. How do you integrate the research from these organizations and academia in your teaching?
Yeah, again, very good. It's a very interesting question because, well, on top of my research, essentially, I teach. It's very common for. I've been doing just research in the past. I was just 100% researcher, but then in the U.S., well, my primary work is teaching. I always try to sort of bring on the table with my students some sort of a smaller scale task that I have in my research to sort of show the students that, well, what's in the textbook, what's in the book is really relevant. It's really helpful to know what's in the book to solve a real problem. And so it's good to have both, like to study the concept, but then to show the students that, hey, this is a real application that I have to deliver. Maybe some students wants to help me, and so I try to involve students in research as much as possible, and as an application of what we study in class. Because really, like, well, there are so many applications that really it's helpful when you do it. When you do it, you really learn. When you hear, yeah, your professors speaking and talking and explaining, it might be interesting, but maybe the day after, maybe forgotten. But if you have to do it, there's a chance that yeah, your attention, the idea of solving a problem will lead the students to really, maybe it's more engaging, and it's more likely that they will remember because they actually did it.
Very nice. This engaging phenomena is very good. And
Mhm.
Professor, what do you think? What innovations are you currently working at your present university?
Yeah, not really. I joined this effort on very popular now GPU computing for AI. So AI is exploiting this parallel hardware name, yeah, commonly referred as GPU. And so in our experiment, we are also, of course, interested into bringing efficiency to the existing software and code. And so I found interesting this task that is about so sort of porting, or sort of partially rewriting code that was written for to be processed by a regular machine in a way that now GPU, those graphic cards, those accelerators, can run it much faster. Um, I think it's in the next. Well, we already see that so the big explosion of AI is really fueled by this, essentially, the idea that we can um, sort of run, well, in the case of for AI, a large data center on large arrays of those accelerator cards that are massively parallel. And so it's a kind of a new, well, not so new, but it's now extensively used. So this is similar to industry. Whenever you have a chance or a room for making your application more efficient, but by running in parallel, uh, that's a good way to sort of yeah, make it more yeah, compatible or more scalable. And so now this period I'm very busy with this.
Very nice. That's good. And the students, what? How do you approach mentoring students in applied physics and in system engineering? What's your approach?
Yeah, I mentor different kind of students because we have I'm involved in different mentoring programs. So depending on the students, then well, there are different strategies. But maybe I think mentoring for me is guiding. And so if you are very young, or you are like a postdoc, um, I think we all need guidance. Me too. And so it's always good. I think mentoring, it's a way to chat with, and to discuss about your maybe future career with a person that maybe already went through that sort of life or steps, and so you can get a little bit more advice and sort of a guidance about maybe what are the options, or maybe what are the strategies to improve the CV, or get maybe a specific knowledge in a specific field, or how to enter into a very, kind of career path. So yeah, I don't know. For me, it's very informal and sort of yeah, easygoing. I think it's more like a chat about things that all the things that happen in life. But I think the mission is really like a sort of a guidance, long-term guidance into what are your objective and how to achieve. What is the most the best way to go to the target.
Very nice. And Professor, one thing, for example, the students in your group, in your area, who want to join your group, or who are joining your group. what's the criteria you have set to select those candidates and they become part of your group?
Curiosity. I think if you are curious enough and if you have enough time to dedicate to a specific challenge, I think that's the only requirement. Knowledge is something you can get almost for free on internet, or you go to the library and get a book. I mean, it's not that it's required a specific knowledge. Knowledge you can gain knowledge while you solve a problem. Sometimes, actually, the most interesting problems I solved, I started without, I didn't know the full extent of the problem. But I guess curiosity is what makes you kind of think, and what makes you like keeps you awake at night, and so that you can read and sort of study and then fix the problem. So I think if you have enough curiosity, enough time to dedicate, and passion, um, I mean, that's good. I think you're all set. Um, so yeah, it's some
Very
sort
good.
of
That's good.
try to
And
be very wide, but it's true that yeah, maybe maybe I don't know, this period is not so common to have students very open minded and very interested into things. So that the other thing is to be. I like to see people like very open minded, so that sometimes the solution to this complex problem requires something that is not really written on the books.
mm,
So it's good to also have very wide experience and not to be super specialistic into just your own garden, but it's good to have a very broad and like some sort of culture.
very
So
nice.
it's a mix.
That's very nice. And Professor, before ending this session, it's really you are the multidisciplinary experts, and also you can see the scientific innovator or global researcher. And before ending this session, what advice do you have for students who are interested in building the multidisciplinary career in science and engineering, especially engineering physics, something, and overall the for the all the students who are in different areas, please?
Yeah, don't worry about your grades. Don't study for the grades. Study something you like, and then while you study something you like, also try to be open, because maybe that's what we call innovation. Is when somebody knows about something, and then it applies to some totally different fields. So it's good to be open, and consider that the best thing you will ever do will require something a little bit beyond what's in the books. So study the books. Don't worry about the grades, but do something you like, and then be open to consider other fields, even if they're not technical. They will help you to solve problems.
Very nice, Professor. Very nice. And Professor Stefano, thank you very much for your time and truly inspiring, definitely. And you are highly practical, I know, and definitely technically rich. And these brilliant insights, and you can say this session definitely help the students to have some insights for their career. Thank you very much, and have a nice time and have a blessed time. Whenever I need your assistance again to be
Sure.
online, I will contact you. Thank you very much.
Thank you. Thanks, everybody.